Welcome to this explainer. Today, we're diving straight into the invisible frontier to uncover the incredible evolution of seafloor mapping technology. You know, our global ocean covers over 70% of the Earth's surface, and yet the vast majority of it remains a total mystery. So, we're going to explore exactly how humanity is working to lift the veil on the absolute largest ecosystem on our planet.
Think about this bizarre paradox for a second. We have highly detailed, incredible topographic maps of distant planets, yet so much of our own ocean floor remains completely hidden in the dark. It's just a stunning reality that despite sending rovers all the way to Mars and probes way beyond our solar system, the deep waters right here on Earth are largely unexplored.
Even with all of our mind-blowing scientific achievements, more than 80% of the world ocean floor remains completely unmapped with modern high-resolution technology. Contrast that with the surface of Mars, which NASA comprehensively mapped to a really high resolution way back in 1999. We literally have a clearer picture of an alien world than we do of our own planetary life support system. It's crazy.
Here is our roadmap for today. We'll cover the alien world below, from ropes to sound waves, painting with sound, mapping from space, and finally, the Seabed 2030 mission.
Section 1. The alien world below. Defining the deep.
So, to truly appreciate this challenge, we first need to understand what it is we're actually trying to map. When we talk about mapping the seafloor, we are talking about bathymetry. Just as topography measures the elevation of land, bathymetry is the study of underwater depth. It lets us understand the submerged, three-dimensional shape of our world. And we aren't just looking for a flat, sandy bottom here. The seafloor features towering underwater mountains, massive coral reefs, sprawling abyssal plains, and really deep oceanic trenches.
To really wrap your head around the extreme scale we're dealing with, consider the Challenger Deep down in the Mariana Trench. It drops approximately 10,935 meters beneath the surface. That is significantly deeper than Mount Everest is tall. We are talking about mapping an environment with extreme pressures, near freezing temperatures, and absolute permanent darkness.
Section 2. From ropes to sound waves. The era of blind probing.
For basically most of human history, finding out what lay beneath the ship was a really slow, grueling task. Around 1800 BCE, ancient Egyptians were simply probing shallow waters with wooden poles. Fast forward thousands of years to the 1870s, and the HMS Challenger expedition used weighted lead lines deployed by winches. Obviously massive upgrade, but still painfully slow. It wasn't until the 1920s and 30s that single-beam echo sounders or fathometers came along. Ships could finally actively ping the seabed, bouncing a single sound wave directly below them to calculate depth based on how long the echo took to return.
But here's the crucial point. For centuries, this method was essentially just probing in the dark. Taking one single depth measurement at a time meant early mariners were just taking spot checks. Between those tiny points of data, massive underwater mountains, hazardous shoals, or deadly drop-offs could easily be missed, entirely hidden from their charts.
Section 3. Painting with sound. The multi-beam revolution.
Modern technology eventually shifted us away from those blind spot checks to sweeping, high-resolution visions of the deep. This is where the multi-beam echo sounder, or MBES, changed absolutely everything. Instead of a single ping that only tells you the depth straight down below the hull, a multi-beam system acts like a giant acoustic flashlight. It sends out hundreds of tightly packed, narrow sound beams in a wide, fan-like swath that can span up to 170 degrees. By doing this, research vessels quite literally paint wide swaths of the seafloor with sound, giving us a continuous, highly accurate 3D digital terrain model in a fraction of the time. And having these high-resolution multi-beam maps actually matters immensely to people living on land. When you compare coastal areas mapped with poor data versus high-resolution bathymetry, the difference is just stark. Poor data generates these erroneous, artificial structures, while multi-beam data reveals the accurate, true landscape. When modeling something as devastating as a tsunami, having the exact shape of the seabed is absolutely vital. The seafloor's terrain directly dictates how tsunami waves will propagate and flood coastal communities, so accurate bathymetry quite literally saves lives. The stakes for having these accurate maps are incredibly high for navigation out on the water, too. Take 2005, for example, when the nuclear submarine USS San Francisco was traveling at high speed and severely collided with an uncharted seamount. The nautical charts they were using simply weren't detailed enough to show this massive underwater mountain hiding directly in their path. It highlighted a really terrifying reality. You cannot navigate safely if you don't know what's right in front of you. Section 4. Mapping from space. The satellite altimetry breakthrough. So, since we obviously can't physically send survey ships to every single square mile of the global ocean, it's just way too vast and expensive, scientists developed a mind-bending alternative. I know it sounds like pure science fiction, but we actually use satellites to map the bottom of the ocean by looking at the top of the ocean. Here's the fascinating physics behind it. Massive underwater mountains have a lot of mass. That extra mass exerts a slightly stronger gravitational pull than the surrounding flat abyssal plains. This extra gravity actually pulls surrounding water toward the mountain, creating a permanent, physical bump on the surface of the sea. Satellite altimeters orbiting the Earth are sensitive enough to measure these tiny variations in sea surface height, which lets scientists reverse engineer the shape of the seafloor miles below. Amazing, right?
A perfect example of this is the recent Surface Water and Ocean Topography, or SWOT, satellite mission. By measuring marine gravity at an unprecedented resolution of 8 kilometers, the SWOT satellite mapped thousands of previously undetected small seamounts and abyssal hills in just over a year of data collection. It completely outpaced decades of older satellite data, giving us our clearest global view of the seafloor yet.
Section 5, the Seabed 2030 Mission, humanity's ultimate quest. Let's dive into the final piece of the puzzle, the monumental, coordinated, global effort to completely lift the veil on this frontier. Thanks to international coordination between organizations, research vessels, and even crowdsourced data from recreational sailors and commercial ships, we have officially mapped 28.7% of the global seafloor to modern, high-resolution standards. Now, while that might not sound like a lot, it's a massive leap from just a few years ago. Every yacht or fishing boat equipped with standard navigation instruments that shares their depth data is actively contributing to this global map.
The Nippon Foundation GB Seabed 2030 project is the driving force pushing to map that remaining roughly 70% by the end of the decade. And the reason this matters goes way beyond just drawing a map. This baseline data is absolutely foundational. We literally need it to understand deep ocean mixing for climate models, to accurately forecast tsunamis, to identify and conserve fragile benthic habitats like deep-sea coral reefs, and of course, to ensure safe maritime navigation for global trade.
To hit this incredibly ambitious goal by 2030, the project is moving way beyond traditional crewed ships. They're leveraging cutting-edge tech, like the SeaKit unmanned surface vessel. These autonomous, unmanned drone ships can be deployed to systematically scan the deepest, most remote, and frankly most dangerous sections of the open ocean without ever risking human crews, which drastically reduces the cost and accelerates the pace of data collection.
The Seabed 2030 mission statement is profoundly clear. Produce the definitive map of the world ocean floor by 2030 to empower the world to make policy decisions, use the ocean sustainably, and undertake scientific research. This really represents one of the most ambitious and unifying scientific endeavors of our time. It completely shifts our perspective from treating the ocean as a dark, dangerous obstacle to understanding it as a shared global resource that is absolutely vital to the health and sustainability of our entire planet.
As we rapidly accelerate our mapping technology, moving from ancient lead lines to autonomous drones and gravity-sensing satellites, we are finally illuminating the final frontier right here on Earth. But it leaves us with an incredibly exciting thought. With over 70% of our dark ocean floor still waiting to be mapped in detail, what undiscovered ancient shipwrecks, bizarre alien-like species, or towering geological wonders are hiding in the dark abyss, just waiting for the light of sound to reveal them? Thank you for joining me on this explainer, and keep your curiosity deep.